All right, we got just a little bit less than a minute left. I'm getting ready to get started. I just want to remind everybody, you do have an online test, test two. Ostensibly, you already had an online test, test one. I did do an extension for one student that told me they had missed it. I am open to giving an extension to anybody else that missed it, but you got to let me know. You will lose points for not doing it on time, but losing points is a lot better than taking a zero. So make sure you guys let me know if you missed test one, which was due not this past Sunday, but the Sunday before that. Online test two was due this coming Sunday, but I went ahead and moved it to being due next Tuesday, specifically because it's taken a little bit longer to cover chapter four than I had hoped. So everybody remember you do have an online test that will be due by Tuesday at 11:59 p.m. I will also remind you that next week is when your first face-to-face test will be due. So what I'll do is I'll make it available as early as Monday morning, and you'll have until basically probably what I'll do is I'll allow it to go until the following Monday. So you could, in principle, have all day Monday, all day Tuesday, all day Wednesday, Thursday, Friday, Saturday, Sunday, and then Monday again to get test one online done. I mean, face-to-face test done. That means you have to find a proctor to do that, or you can show up at my class on Wednesday, which is the day I'll be doing the test. There'll be a bunch of different times you can come to the Virginia Beach campus to take your test with me, but you could take it with me instead of having to go to a testing center. Otherwise, you can go to one of our testing centers for free. Or if you're not near one of our campuses, there's other colleges and schools near where you are that could, in principle, proctor a test for you. There's also online services that can proctor it for you. All of those have to be cleared with me, and you have to sort of get that stuff straightened out before basically this week sometime. So make sure you guys start looking for who you're using to proctor your first test. There are specific guidelines. If you end up having a third party do it that's not, a university or a school, then there's a whole process where they've got to fill out a form, they've got to email it back to me, I've got to approve it, I got to answer questions, they got to answer questions, and then all that stuff. So that can take a bit of work, but you guys need to be starting working on that right now. So all right, it's now 5:32, so I'm going to go ahead and get started. I just want to remind everybody, like I just said, you have an online test due Tuesday at 11:59 p.m. You have a face-to-face test that will be due somewhere between Monday, this coming Monday, and the following Monday. That's the absolute latest you can take it. You've got to find your own proctor, or you can show up on Wednesday and take it with me in one of my classes. I will have a time slot probably somewhere around 10:30 in the morning. I'll have another time slot somewhere around noon. I'll have another time slot somewhere around 2 o'clock. And that'll be your only chances to take it with me as a proctor, and that would require you to come to the Virginia Beach campus. Everybody has to have a freestanding scientific calculator. You can't use one on your iPad. You can't use one on your iPhone. You actually have to have a scientific calculator. Uh, if we actually take it on the computer, and I'm not certain that's the case, then you could, in principle, use the scientific calculator that comes with the operating system. But some test proctors won't allow that, in which case you'd be unable to do it. The test does come with the equation sheets and the facts from the front cover of the textbook, as you can see in the helpful documents and links. So check that out. Uh, Again, everybody chat me your first and last name for attendance, and I'm going to go ahead and get started. So we are on chapter four, and chapter four is about Newton's laws of motion. Newton's first law said an object in motion tends to stay in that state of motion unless acted upon by a net external force. And the simplest way to say that with a fewer words would be an object maintains a constant velocity unless acted upon by a net external force. Net, remember, means add up all the forces acting on it External means only count the forces that other objects are applying to it. You can't count a force that something puts on itself. So that's why I mean external. And non-zero just means that when you add up all the forces vectorially, the answer comes up to something other than zero. So if the answer comes up to zero, then the velocity will be a constant. That means it can't change speed, it can't speed up, it can't slow down, but it also can't change direction, even if it's kept the speed constant. That's Newton's first law, which is very, very much equivalent to Newton's Galileo's law of inertia. Newton's second law is that the acceleration an object will achieve is parallel to the net external force applied to the object and directly proportional to the net external force acting on the object and inversely proportional to the mass of the object. So that gives us the summation of forces equals mass times acceleration, which is really a vector equation. That's Newton's second law. And then finally, Newton's third law is for every action, there's an equal but opposite reaction, or in equation form, I just wrote that as F subscript A B is equal to negative F subscript B A. And those two vectors or those two F's are have a little arrow over them because that's a vector equation. The negative just tells you that they point in opposite directions, and the AB versus BA in the F equals in the FAB, that means the force on A due to B, and in the FBA means the force on B due to A. So that's something to keep in mind. Action reaction pairs are always forces acting on two different bodies, so they never should be able to be added together or subtracted from one another. And not only that, any two forces, even if they happen to be equal in magnitude but opposite in direction, if they're acting on the same object, they are not action reaction pairs. So the example I gave you, for instance, is my weight is about 250 pounds. That's the force on Mr. Younger as a result of the Earth. So we call that FBE, for instance, for force on Billy due to Earth. Now, the action reaction pair to that one, we've already said FBE is the force on Billy due to the Earth. Well, I need to reverse those. And that tells us the reaction pair to that force is the force on the earth due to Billy. So my 250 pounds of weight is gravitationally attracting the earth to me, pointing towards my direction, and that force is net is 250 pounds, but pointing up towards me, whereas my weight pointed down towards the center of the earth. All right, so that's a recap of our laws. Not only that, I'll remind you that the first law is the one that allowed us to generate the idea of a normal force. So, for instance, if this is sitting on a tabletop, this Rubik's cube here is sitting on a tabletop, and we see that it's not accelerating. So, according to Newton's first law, since it's not accelerating, the total force must be zero. Well, we already know that there's a force called the weight of this object, and that would point down. That's the mass of this times g. That would point down. But since Newton's first law says that it's not accelerating, therefore the net force must be zero, that means there must be at least one other force acting on it. And if it is one other force, then that force exactly cancels out the weight force. That reaches or causes us to reach the conclusion that the table, even though it's an inanimate object, is pushing up on the Rubik's cube with a force equal in magnitude to the Rubik's cube's weight, but pointed oppositely because the weight points down. This would be the normal force pointing up on the object. Notice the weight of the Rubik's cube is a force on the Rubik's cube and it points down. Notice the normal force is a force on the Rubik's cube but it points up. So those are not action reaction pairs, but either way we were able to reach the conclusion that a normal force exists. So let's start off with example 4.6. I've taken the time to write these. I'm going to share my iPad screen. Anybody have any questions before we get started other than ones you might have already asked? Actually, I don't think anybody
Yeah,
already
I have
asked
a
me.
question.
Yes.
I have a question, Professor. Were you saying that we have a test that we have to take by Tuesday in regards to the proctor? And I wonder, can you please explain it one more time?
Yes. So You do have a face-to-face test. I don't know why this isn't working. Let me try this again. You do have a face-to-face test that has to be done next week. That one's going to require proctoring. But you also have Tuesday at 11:59 p.m. It was due this coming Sunday at 11:59 p.m., but I moved it back to Tuesday. That was an online test. And online tests are open book, open notes. The only thing you have is some time constraints, and you're not allowed to actually look at any document that's been created since I posted that test. That's just me trying to say, hey, you're allowed to look at notes, you're allowed to look at textbooks, you're allowed to do Google searches on the internet. You just can't find some way of sort of circumventing that by someone creating a website after they've taken the test, they've looked at it, they've made some ideas of what the test is about. Now they make up a website to help you, and then you go and look at that. That would be cheating. Okay. But that being said, you're completely allowed to do a Google search for answers online. You're allowed to look through your notes. You're allowed to look through your book. You're allowed to look through other books. You're allowed to look through other notes. Again, as long as you're not looking at notes that were made after I released the test, which was Monday. Okay. So that's the rules on the online test. You got to have that done by Tuesday at 11:59 p.m. The face-to-face test, you have to have a proctor. That means you have to find someone that can monitor, watch your test. And normally there's testing centers that do this sort of thing. So if you are taking this online, you might not be near a TCC campus, but chances are there is a college or school near you that could offer proctoring services. Uh, the proctoring services at TCC campuses are all free, so that's a free option. You can go to whichever campus is closest to you. In addition to that, I am giving the test on Wednesday. So you will have various times Wednesday during the day that you could show up at the Virginia Beach campus, and I would proctor for you. Or if you can't fit that in, nor any of the times from any of the TCC campuses, then you're going to have to find a proctor on your own to take this test. Okay.
You said a proctor, like, can we use is it a responders lockdown browser thing? We can do it
That's
like
not
that, or
sufficient. We've got to do more than that. There is a way I could do it online, but you would need like a mirror. You would need a computer and a cell phone, both of which have cameras on them. But that's another way it could be done. It's just that that would take a little bit more work, and I'd have to explain some of the details for you. But yeah, you could do that.
thank you.
No problem. All right, so I'm going to try to share the screen again. I don't know what happened last time, but it did not act like it was supposed to, so I'm going to try to do it again. Okay, now let's see if it lets me. Hmm. What Wi-Fi am I on here? Okay, I'm on the right Wi-Fi there. Let's see what Wi-Fi I'm on up here. Aha, I'm on different Wi-Fi. That's why it didn't work.
Prof, we could just email you for the test times, right? Face to face.
What are you asking about now?
Oh, we could just email you for the test times for the times
Yes,
that
I'll
we.
be sending out an email letting you know what test times I have available for the proctoring, and you just let me know that you're coming to that. That'd be great. And even then, you can just still show up.
Okay, perfect.
Okay. All right, I finally got it on. Evidently, my iPad had switched Wi-Fi's. So, example 4.6, a 10-kilogram box is sitting on a flat horizontal tabletop. A, determine the weight of the box and the normal force exerted by the table on the box. B, if a person presses down on the box with a force of 40 newtons, what is the normal force? And then C, if the person instead lifts up on the box with a force of 40 newtons, what is the normal force? So I'm going to draw those three scenarios as free body diagrams. And generally speaking, a free body diagram includes a coordinate system, like here I've drawn X and Y, and a point to represent the actual object. So that red dot there represents the box. Until we cover torque, we're not going to be able to treat the objects as bigger than microscopic point particles because if, for instance, the object was this pin, then it would matter whether the force is here or here or here or here. In order for us to take that into consideration, we have to understand something called torque. We're not doing that. So what we're doing right now is pretending all things are point particles. Now, the mass of this object I'm going to write over here, and that's 10.0 kilograms. Now, the forces acting on it are going to be the normal force, which points in the positive y direction. So I'm labeling that green as if green for a green light to go. And then the weight is pointing down. That's a negative direction, and that's W equals. Remember, W is equal to M times G. So M in this case is 10. So this gives me 98.0 newtons. That's the weight. So that's the case in part A. Then in part B, we'll have a slightly different scenario. In this scenario, we're going to have a normal force pointing up, but we're also going to have a person pointing downward or pushing downward on it. So what we have here is a force of 40.0 newtons pointing down. And then we have another force, the weight, which is equal to 98.0 newtons. And then finally, for part C, we're going to have another coordinate system, of course. There's our point particle. Now this time we have a normal force, again pointing up, that's F sub n. But in this case, we have a force that's also pointing up, and that's 40.0 newtons. And then, of course, we still have the weight, which is W equals 98.0 newtons. So that's the three scenarios we're dealing with. Notice how I've drawn the free body diagrams. It does help to use some colors to represent positive components and maybe use a third color to represent a vector that isn't parallel to either axis. So then it would make sense. Hey, if I see a vector that's not red or green, I know that that particular vector needs to be broken down into its components in the x direction and components in the y direction, and then those can be in red and green. Those are all really good, helpful things. So let me start off with our solution. Now, what we're applying here is Newton's second law, and that says the summation of the forces is equal to mass times acceleration. Now, in three dimensions, that means you've got a summation of forces in the x direction equals mass times acceleration in the x direction, another one for the summation of forces in the y direction, and another one for the summation of forces in the z direction. In this case, I'm only dealing with y direction, so that's all I need to deal with. So with that in mind, I'm going to say A, according to Newton's second law, my forces are the normal force pointing up, so that's positive. Now remember, Newton's second law has that sigma. That means add up all the forces. So I'm doing nothing but adding, but sometimes the components are negative, so it'd be plus or minus. I'm not always going to take the time to write the plus sign and then the minus sign there. I'll just write it as if it's subtraction, but I want you guys to realize that Newton's laws say we add up the forces on the left, and they're set equal to mass times acceleration. Now, I'm also going to point out that this box, this 10 kilogram box, is not moving. So the y component is zero, or the y position variable is zero. And if you wait a split second, it's still zero. If you wait another split second, it's still zero. So that means the acceleration is going to be zero. And that's the case for all three of these. So Newton's second law becomes Fn minus, oops, might help if I write instead of highlight. So this is plus negative 98.0 newtons is equal to 0. So that literally means that the acceleration in the y direction is 0. That's why I've got the 0 there. This allows me to solve for the normal force, and therefore the normal force is positive 98.0 newtons. Okay. Now, I've already answered the question about what the weight is. Weight, and let me go ahead and write this here. W is equal to mg, which equals 10.0 kilograms, times gravitational acceleration on Earth, which is 9.80 meters per second every second. So this gives me 98.0 newtons. So that's the W as well. So those are my answers for part A. Now for part B, again, I have Fn is pointing up. Then I've got, normally I would take the time to write plus and then a negative sign, but I've already explained that to you. I'm always only adding on the left-hand side, so I'm going to skip that step and just write minus 40.0 newtons minus 98.0 newtons is equal to 0. So now you see that the normal force works out to be 138.0 newtons. Everybody see how I got that? Anybody have any questions on that? Okay, here's C now. And for C, what we have is F normal pointing up, but we also have the 40 newtons pointing up, so that's going to be plus 40.0 newtons, and then minus 98.0 newtons, and all that's equal to 0. So in this case, we get that the normal force is in fact equal to, when I pull the 98 to the other side, that's going to make it a positive 98. And then when I pull the 40 to the other side, that's going to make it a minus. So 98 minus 40 is 58.0 newtons. So that's the answer to part C. The normal force is just going to be 58.0 newtons. So this problem was mostly instructive. I wanted you to understand that in a lot of cases, the normal force is just the weight of the object. Uh, we saw that in part A. It turned out to be exactly the weight of the object. But in part B, we saw that, hey, if you actually add an additional downward force on the weight or on the mass sitting on the table, then the normal force is going to have to compensate for that. That makes sense. Like if you found out that a table could hold 300 pounds and you went ahead and stuck a 298-pound chunk of metal on it, then you're automatically really close to making the table fail. Now, if you took a small child and put it on top of it, assuming the child weighs more than 2 pounds, which is highly likely, then you're going to exceed the capacity of the table and it's going to actually break, because now the normal force has to compensate not only for the 298-pound chunk that you put up there, but for also the kid. So when you add an additional weight to an object, that makes the normal force go up. And similarly, in part C, if you have a component of force pulling up on it, that reduces the burden of the table, and therefore you get a smaller normal force. Anybody have any questions on that?
I was trying to catch up writing.
Uh-huh.
And so I was looking back at the A graph, and the 10.0 kilograms, is that the Newton, like the force of the Newtons? Like, is that the green
That's the
portion?
mass part of it. So the newtons is the force, and that's the weight, that's the affinity that gravity has for it. But the
Okay.
kilograms is its inertia, or its reluctance to change its motion, its reluctance to accelerate. So mass is a scalar quantity measured in kilograms in the SI system, and the vector quantity is the weight, and that's mass times gravitational acceleration, and that has units of newtons in the SI system.
Okay, okay. Yeah, I'm seeing it now. I think
Okay.
I was trying to copy too much at the
Yeah,
same time.
yeah, that's perfectly
Okay,
understandable.
okay. Okay, so yeah, so I see that C, that was 40 newtons, and that's why it's up, the upward.
Exactly.
Okay, because they're lifting. Okay, all right.
Okay.
Yeah.
Now, we'll later see, because I'm going to do an inclined plane, and you'll find that that's another time where the normal force isn't just equal to the weight. It's something entirely different. So you'll see over, many, many examples, you'll see how that normal force changes. But you've now learned a couple things. The normal force is always perpendicular to the surface it's sitting on. That's one thing. Uh, if there's no other forces acting and the table that it's sitting on is horizontal, then you'll find that the normal force is equal to the weight. But if you add a force pushing downward on it, then that's going to make the normal force get larger. Or if you add a force that's lifting up on it, that's going to make the normal force get smaller. So that's a couple ways we've changed it. But for instance, if I were to take a box and push it hard horizontally up against the table, I mean, up against the wall. In that case, the normal force would actually be horizontal, and it doesn't have anything to do with weight whatsoever. It's basically however much force I'm pushing it in, that's what the normal force has to respond by. So that's another way you could change it. And you'll see later when I do an inclined plane, that's yet another way of changing it. Any questions on this one before I go to the next example?
Why did we assume the acceleration is zero?
We didn't. We just have the idea of a 10 kilogram box sitting on a flat horizontal table. If it's sitting on a table, that means the y coordinate shouldn't be changing. And y coordinate not changing means the velocity zero. But as we learned in previous chapters, the velocity being zero doesn't necessarily mean the acceleration is zero. But if the velocity is zero and then you wait a tenth of a second and it's still zero, then you know the acceleration is zero.
Thank you.
No problem. All right, let's look at example 4.7. If the 10 kilogram box was pulled upward with a force of 100 newtons, what would happen? So this is that same box, only now because I'm lifting up with it. Remember, we found the weight was 98.0 newtons. Now I'm lifting up on it with a force of 100 newtons. That's greater than the weight, so there's not going to be any normal force. It's literally going to be up off the table, or at least it might still be touching the table, but the table's not putting any force on it whatsoever because it can't. I've pulled up on it so much that there's no weight left to push down on the table. So here's my free body diagram for this one. I have 10.0 kilograms. I have 100.0 newtons pulling up on it. And I have W equals 98.0 newtons acting downward on it. So, solution, the summation of the forces is equal to mass times acceleration. In this case, is just going to become the summation of the forces in the y direction is equal to mass times acceleration in the y direction. And in this case, the y direction could act, or the y position could actually change. That's what we're trying to calculate. So I'm going to go ahead and write down what we have. What I have is 100.0 newtons plus negative 98.0 newtons. Notice I did take time to write addition and then put the negative sign on there because it's a whole nother problem. I just wanted to remind you that's what's going on. That's all the forces acting on it, and that's the purpose of the free body diagram, is where we can split out all the junk that we're told, drawings and all that stuff. We're going to just reduce it to a dot, and we're going to reduce it to some vectors, and then only those vectors that are forces acting on it need to be included. And in this case, that works out to be 10.0 kilograms times a. Now, I would normally say a sub y, but that's the only acceleration we're dealing with, so y subscript it. Now, when I take 100.0 newtons minus 98.0 newtons, I get 2.0 newtons is equal to 10.0 kilograms times A. So that tells me that A is in fact equal to 2.0 newtons divided by 10.0 kilograms. And a newton is a kilogram meter per second squared. So when I divide it by a kilogram, I just get a meter per second squared. And this is in fact 0.20 meters per second every second is equal to the acceleration. So what this means is when I applied a 100 Newton force upward on the 10 kilogram box, that exceeded the weight of the box. So the box would not need the table at all and therefore does not have a normal force. And in fact, it had a surplus of force so that once I subtracted the weight from it, I still had 2 newtons left over. And when I plugged that into Newton's second law, that told me that the object will actually accelerate upward at 2 meters per second, or excuse me, zero point 0.2 meters per second every second. Now, remember, all of this builds on what we learned in chapter 2 and chapter 3. So I could say, if this state was maintained, how fast would this block be going or this box be going after 1 second? And if we assume that the box was initially sitting still, then the acceleration being zero point 0.2 meters per second every second means that after 1 second, it'll be going upward at a velocity of zero point 0.2 meters per second. After 2 seconds, it's going to be going a velocity of zero point 0.4 meters per second. And after 3 seconds, it's going to be going a velocity of 0.3, or excuse me, 0.60 meters per second. Okay. And then you could also use that to calculate how far it would go using x equals 1 half at squared plus v0t plus x0. All of that stuff's still fair game. So I just want to remind you about that. Anybody have any questions on that problem?
Do you just memorize like some of these like the Newton over kilogram equaling meters per second squared? Like you know that A is going to have to be that, but is it just like a memorization
It
like
is.
technique?
It's memorization just by overuse. You know, sometimes you never take the time to actually memorize certain things, but because you do them so much, they just get stuck in your brain. That's pretty much
Yeah.
what's happening.
Okay. Okay.
Yep. I will say that I discovered some time ago that memorization sometimes is really helpful. Okay. Don't forget, we can add kinematic follow up questions. So
Professor,
that's
I
what I
got a
would say.
question.
Yeah, go ahead.
So I got a question for the unit that goes with the answer.
Hmm.
If I put like Newton per kilograms, is that incorrect? Or I have to put meters per second per
No,
second.
technically it would be correct to say newtons per kilogram. If I were to give you a multiple choice test, you don't have that freedom because the multiple choices would have the answers that you want. But unless I explicitly told you to give me the answers in another unit, like meters per second, then yeah, you're completely free to write it as newtons per kilogram. Did that answer your
Thank
With
question, Ben? That was Benjamin,
Yes,
right?
sir.
Okay. So I'm just wanting to point out that
with
this is the same thing as 1 kilogram times a meter per second squared. So that's what a newton is. Good questions, you
oh
guys.
yeah. Okay.
Did you have another
I have
question,
a
Michelle,
with
or whoever's talking?
yeah, yeah. With the tests,
Hmm.
if we are showing our work, do we like if we got the answer wrong, could we still gain points back from that? Or I guess how do you grade those?
Yeah, that's the problem with the multiple choice tests. And I've had some
Okay.
students taking advantage of me lately, so I'm leaning towards getting rid of multiple choice tests. But when I do a multiple choice test, then pretty much you get the answer right, you get full credit. You get the answer wrong, you get zero credit.
Right.
I'm going to try to implement it where I don't necessarily do the multiple choice, and then that way I can give you partial credit. But that means the number of questions on the test might only be 4 or 5, whereas they used to be like 18 or 20.
Okay. Yeah, that makes sense.
Okay. All right. So, example 4.8, a 65 kilogram person stands on a scale that reads in kilograms and is in an elevator, meaning the scale and the person are in the elevator and the person standing on the scale. If the elevator descends, that means go down, with an acceleration of 0.20 g, that means zero point 0.20 times 9.8, what will the scale read? B, what is the weight of the person? And C, what does the scale read when the elevator descends at a constant 1.0 meters per second? Okay, so I'm going to start off by drawing a little picture to make some sense of what this is. So what we can imagine is an elevator box that looks something like this, an elevator car. And we got a little scale in the bottom. And there's the little uh, plate that you'd put your weight on. In this case, the weight is a person, and the mass of this person is 65 kilograms. And the object is going down this way. So the elevator's descending. In one case, we have for part A, comma B, we have A is equal to negative 0.20. And I say negative because I'm treating downward as the negative y direction, and I'm going to treat upward as the positive y direction. So I'm going to say it's negative 0.20 times 9.80 meters per second every second. That's going to be uh, negative 1.96 meters per second every second downward is the acceleration that we're going to experience. Now I'm going to draw a free body diagram. Now, the drawing I have is pretty close to a free body diagram, but it's not quite. uh, I want to simplify the diagram quite a bit from what's on the left versus what's on the right. So what I'm going to do is I'm going to represent the person as having a mass of 65 kilograms, and acting on them is a vertical force pointing upward. That is the force that the scale provides. So I'm going to call this F sub S, which equals force of scale. So, meaning the force that the scale is actually applying. Now, in addition to that, we've got the weight of the person, which is W equals mg. Now, 65 times 9.8 is what we're talking about here. So when I do that, I've got 65 times 9.8 gives me 637 newtons. So that's the actual weight. And then over to the side here for part A slash B, we have the acceleration equal to 1.96 in magnitude. Okay. So what I want to do now is I want to write Newton's second law. The summation of the forces in the y direction is equal to mass times acceleration in the y direction. So the forces I have acting, according to this, are the force of the scale. Now that's going to give me what the scale would read if it read it in newtons. So then when I'm done with that, I divide it by 9.8, and that'll give me the mass, the scale, what the scale would read in kilograms are in units of mass. So I'm looking at Fs minus 637 newtons is equal to 65 kilograms times, now the acceleration is actually downward for part A and B, so I'll write A/B here. So the acceleration is negative 1.96 meters per second per second. So now I've got F sub S minus 637 newtons is equal to 65 times 1.96 gives me negative 127.4 newtons. Therefore, I get that the scale force, I just wrote a S there by mistake, that the scale force would be, in fact, equal to 637.0 newtons minus 127.4 newtons. That gives me 509.6 newtons. Now, technically, we only had two sig figs, so really this digit and this digit are not sig figs. And far as the 637 goes, or excuse me, far as the 127 goes, the 7 and the 4 were not sig figs either. So really, the 9 and the 6 are not sig figs. So we're talking roughly 510 newtons. Now, the scale reads in kilograms. Therefore, F scale in kilograms would be 509.6 newtons divided by the mass, which was 65 kilograms. Excuse me. Divided by 9.8, not 65. Sorry about that. Divided by 9.80 meters per second per second. So 509.6 divided by 9.8 gives me 52 kilograms. So the scale will read for part A, the scale is going to read 52 kilograms. Part B, I asked what was the weight of the person. Well, we already did that as well. So W is equal to the 637 that I got. So that's part B. Now, in part C, it says, what does the scale read when the elevator descends at a constant 1.0 meters per second? Anybody have an answer or thought about what that answer is? Anyone? Okay, so remember, it's not accelerating at all because it's moving at a constant speed of 1.0 meters per second. Because of that, we now get, for part C, we now get F scale minus 637 newtons is equal to 65 kilograms times 0 meters per second per second. That means the force on the scale would actually read 637 newtons, except it reads in kilograms. So the scale reads 65 kilograms for part C. Anybody have any questions on that? Now, go ahead.
The 65 was coming from.
If you take 637 and divide it by 9.8,
Okay, all right. Thank you.
Gotcha. Yeah, so if you ever have a scale that's supposed to read in newtons, then you take the kilograms and multiply by 9.8. If you have a scale that reads in kilograms, then you're going to take the scale reading in newtons and divide it by 9.8.
That makes sense. Thank you.
Okay. Now, I also want you guys to think about this. An acceleration of 1.96 downward, that could happen from an object going down but slowing down. But it could also happen because notice it's making it lighter. It could also happen if you're going up but slowing down on the way up. Okay, so remember the acceleration equation that we had, the average acceleration is v final minus v initial over t. We have to get a negative answer. And the ways you could do that is you can either point downward as positive and get one answer, or you could call upward as positive and get another answer. So keep that in mind. What we discovered here was that because the person was accelerating downward, the scale didn't have to have such a large burden to hold the person up. It only had to hold a fraction of its weight. So it read it as if the person only weighed 52 kilograms when in fact they weighed 65 kilograms. You can also feel that if you are on the way up in an elevator and just before it comes to a stop. So say you're going to the 10th floor. Once you see you're crossing the ninth floor, if you take and jump upward, what you'll see is the elevator will start to accelerate downward, meaning it's going to slow down and you'll feel lighter than air and you'll actually be able to jump and your head will almost touch the top. I do that all the time. Like when buildings are closed, I used to take my daughters out to whatever school I'm working at or some building and we'll go on the elevators and I'll jump up just before we get to the top or just before we get to the bottom. I'll jump up really high and then that allows me to get slammed down really quickly. So that kind of stuff. Do that. Use your everyday life. Every time you get a chance to ride an elevator, notice that instantly when it takes off in the upward direction, you feel like your knees have to strengthen up a little bit to keep your legs straight. But then when you get near the end of your trip up, you'll feel that your legs are a little bit lighter. They're under less of a burden as the elevator starts to slow down. All right. Now, the next examples are ones that I sort of created myself. They're very much like examples in the book, but I'm showing certain things. So this one says, consider the train of boxes shown below. What is the acceleration of each box and what are the tensions in the ropes connecting the boxes? So what we have here is a 30 kilogram box with a force pulling to the right of 100 newtons, but that 30 kilogram box has a rope tied to it, and that rope is tied to a 20 kilogram box. And then that 20 kilogram box has another rope tied to the other end, and that rope is tied to a 10 kilogram box. Now, one thing we can do is we can treat this whole thing as if it's one big object, an object that has a mass of 30 kilograms plus 20 kilograms plus 10 kilograms gives me 60 kilograms, and I'm assuming the mass of the ropes is zero. Okay. That's something we often do, not because reality allows us to have massless ropes, but because the mass of the rope is usually smaller than the masses you're dealing with by a factor of 10 or more. So, for instance, if I'm dealing with a 30 kilogram box, or even the smallest is a 10 kilogram box, if the rope weighed less than 1 kilogram, then I could assume the rope is massless. That's our rule. A factor of 10 is good enough to assume zero. That being said, I'd prefer a factor of 100 or at least a factor of 20 or 15 or 30 or something like that, but 100 would definitely be even better. All right. So what I'm going to do is draw a free body diagram for each of these. And technically, you're going to have a free body diagram in the X direction and the Y direction. But right now, since we haven't yet learned about friction, we're not going to care too much about the normal forces. I've already given you enough of what I think you need to know about normal forces, so I'm not going to waste time calculating the normal forces on here. I'll show them on the free body diagram, but that's it. So first thing I'm going to do is I'm going to say this is a 10.0 kilogram mass. it has acting on it a normal force Fn1, but it also has acting on it a weight, which is 10 times 9.8 would be 98.0 newtons, like that. And then if you were sitting in that box, maybe the box has glass windows or whatever, you would feel yourself sitting perfectly still. And then all of a sudden you'd see that rope in front of you tighten up and almost try to stretch. And then all of a sudden you would take off being pulled forward. So in your world, it seems to you that that tension in the rope, oops, I should write that as green. Sorry about that. That tension in the rope, which I call T12, that T12 is what's responsible for moving me to the right. Okay. So you can see here the summation of forces in the y direction would give me 0 because we're not expecting the box to bounce up and down. So the y coordinate's not only 0, but it's going to stay 0. Therefore, the acceleration in the y direction is 0. But I'm not even going to waste my time writing that. I will waste my time writing, and it's not really a waste, but writing the summation of forces in the x direction equals mass times acceleration in the x direction, like that. So when I do this, I only have one force acting, and in fact, what I get is T12 is equal to 10.0 kilograms times A. Now, if I assume that the rope does not stretch and doesn't get slack, then if I move that 30 kilogram box 1 inch to the right, then the 20 kilogram box is going to move 1 inch to the right, and the 10 kilogram box is also going to move 1 inch to the right. So that means the X for the 30 kilograms, the 20 kilograms, and the 10 kilogram are all the same. Now, if I move that 30 kilogram box 1 inch to the right in 1 second, then the 20 kilogram box would move 1 inch to the right in 1 second, and the 10 kilogram box would move 1 inch to the right in 1 second. That means the velocity of the 30 kilogram is equal to the velocity of the 20 kilogram, and that's equal to the velocity of the 10 kilogram. Now, if I go a little bit further and I imagine pulling the 30 kilogram to the right 1 inch in 1 second and then 2 inches in the next second, then the 30 kilogram box would actually be accelerating. But the 20 kilogram box would do exactly the same thing, so it would have the same acceleration, and the 10 kilogram box would do exactly the same thing, so it would have the same acceleration as well. So that's why I'm not writing any different accelerations. I'm just going to write them all as A. This is going to be equation 1, and I'll make use of it in a second. Now I'm going to write another equation for the 20 kilogram box. Here's X, here's Y. This one is 20.0 kilograms. I have acting on it a normal force Fn2 and a weight, which would be 196 newtons. But those don't matter. Those are in the y direction. But what I do have is, according to the 20 kilogram box, the rope has a tension T23 that tends to pull that 20 kilogram box to the right. But if you were in that 20 kilogram box, you would realize that the rope behind you is slowing you down. So in addition to that, I'm going to have T12 as a force that's pulling to the left. Now I can write Newton's second law again. The summation of the forces in the x direction is equal to mass times acceleration in the x direction. In this case, what I'm going to get is T23 minus T12 is equal to 20.0 kilograms times A. And again, I'm not subscripting the A because we just made the argument that there's no need to. So this is equation 2, and this is equation 1. And I'm only underlining them so you won't get confused as to where the equation 1 ends and where equation 2 starts. I didn't want to box them off because that would give you the impression it's a final answer. It's not that, but hopefully that is clear to you guys. Now I'm going to do a free body diagram for the 30 kilogram box. In this case, I've got 30.0 kilograms. I've got a normal force acting up, that'll be F in 3. And I got a weight acting downward, which will be 294 newtons, like that.
Would
Now,
you
in
like to
addition to that, I have a 100 Newton force pulling to the right. And I also have, according to the 30 kilogram box, it thinks that rope T23 is actually slowing it down. So notice the T23 is pointing to the left on this case. So what I have now for the summation of the forces in the x direction equals mass times acceleration in the x direction. For this case, I've got 100.0 newtons minus T23 is equal to 30.0 kilograms times A, and that's going to be equation 3. Okay? So, in principle, I could go ahead and write a Newton's second law for the whole big thing, and that would actually allow me to solve for this acceleration all by itself, but I didn't want you to think that you ever have to do that, so I'm going to go ahead and solve this as it is. What I'm going to do first is solve 1 for T12 and plug that into equation 2. So in doing that, what I get is T23 minus 10.0 kilograms times A is equal to 20.0 kilograms times A. So now I can see that T23 is equal to 30.0 kilograms times A, and I'm going to call this equation 4. Okay, so by plugging 1 into 2, I was able to eliminate the T12 unknown, and now I have T23 and A as an unknown. Now I'm going to plug T23 into equation 3. In other words, I'm doing the same thing again, only now I'm doing it with the new result I got. So in doing that, I'm going to get 100.0 newtons minus T23, which is 30.0 kilograms times A, is equal to 30.0 kilograms times A. So what you can see now is that you're going to get 100.0 newtons is equal to 60.0 kilograms times A. Therefore, A is equal to 100.0 newtons divided by 60.0 kilograms. And of course, that is the same thing as 10 divided by 6, which is 1.6667 or whatever. So this is going to give me the acceleration is equal to 1.667 meters per second is equal to A. So that's the acceleration of each of those boxes. Now, we only had 4 sig figs divided by 3 sig figs, so technically speaking, this 7 is not a sig fig. Okay? But now I can also solve for T23 by using 4. So equation 4 gives me T23 is equal to 30.0 kilograms times 1.667 meters per second. So 30 times 1.667 gives me 50.0 newtons. And that's equal to T23. Now you'll notice that's exactly the force that I would need to accelerate the 20 kilogram plus the 10 kilogram box at 1.667 meters per second. So that makes some sense. Now I can figure out T12 from equation, excuse me, from equation 1, T12 is equal to 10.0 kilograms times 1.667 meters per second, which gives me obviously 16. Whoa, gives me 16.67 newtons is equal to T12. Okay. So that's how we were able to solve that three body problem. Now, I should point out that you didn't actually have to do that. We could have just started off with the whole object and we would say 100 newtons is equal to 60.0 kilograms times A, and that would give us A equals 1.66 meters per second. So I could have done that as well. But when you do that, when I treat the whole object as if it's one big thing, then I have no ability to figure out the tensions because those are internal forces. So I could have done that to just figure out the acceleration. Then I could have plugged the acceleration into equation 1. That would have gave me T12. Then I could plug T12 into equation 2 and plug in A, and that would allow me to figure out T23. Okay, so that's a whole nother way I could have done it. Anybody have any questions on that? All right. An object of mass m is placed on an inclined plane of inclination angle theta. Assume the inclined plane is a frictionless surface and compute A, the normal force, Fn, B, the force that causes the mass to slide down the incline, and C, the acceleration of the mass. Okay, so when I state something like that, where I say an object has a mass m, you're supposed to assume, oh, m is one of the variables I know. I'm not going to give you a number for it, but you're going to work with it like you know it. So the same thing for the angle theta here. So let me draw a picture so y'all understand what I'm talking about. What we're looking at here is an inclined plane for which this is the angle theta right there. And now we're going to imagine that this is a box of mass m. Now I'm going to, since this is on an inclined plane, it turns out that when you have a problem to be solved on an inclined plane, almost every time it's better to tilt your coordinate system so that your x-axis is parallel to the incline and your y-axis is perpendicular to the incline instead of having the x-axis perfectly horizontal and the y-axis perfectly vertical. So, with that in mind, I'm going to do that now. I'm going to draw a free body diagram with this as my x-axis, and that is my y-axis. And like always, we're going to assume the object is a point particle, but it has a mass m. Now, the forces acting on it, of course, are the object's weight, and I'm drawing this with a black vector because this vector W is equal to m times g, but it hasn't been rendered to be a component parallel to the x-axis or a component parallel to the y-axis, so I don't want to use red or green at all for that. Now, the other force acting on this is the normal force, and that one is obviously parallel to the y-axis. So that's my normal force, Fn. Now, I also need to point out that this is the angle theta. Therefore, this angle right here is 90 minus theta. Can anybody tell me now what this angle is? The little purple one I just drew?
Is it 30 minus theta?
Exactly. That should be the theta. Because if you imagine theta was 30, the red angle 90 minus 30 would be 60. And then you see that this angle from here to here is 90 degrees. So if this is 60, this one must be 30. Or if this one's 90 minus theta, this one must be theta.
Yeah, that
Every,
makes sense.
everybody follow that? Now that's something really important because this inclined plane diagram is going to appear over and over again, not only the first semester, but also the second semester and maybe even the third semester. Okay. Now, what I'm going to do is break this weight vector up into two components, a component parallel to the y-axis and a component parallel to the x-axis. Well, the component parallel to the y-axis is actually in the negative direction, so I'm going to use red for that. And the component parallel to the x-axis is actually parallel to the positive direction, so I'm going to use green for that one. Okay, now I've got to use trigonometry. What I know is that the sine of theta is equal to opposite over hypotenuse, and the green is the opposite, so that's W sub x over mg because mg is the hypotenuse. Similarly, cosine theta equals adjacent over hypotenuse, so that's going to be W sub y over mg. So now I can see that the red here is mg cosine theta, and the green is mg sine theta. Okay. So if you assume that this box is going to slide down the incline, then the y variable is not going to change. And since the y variable doesn't change, that means the velocity in the y direction is zero. And if the y variable still doesn't change, that means the y velocity is still zero. That means the acceleration in the y direction is zero. So now I can say the summation of the forces in the y. And by the way, when we tilt them, we often call it x prime and y prime. So I'll just use that here to keep it a little simpler for you. So the summation of forces in the y prime direction is equal to mass times acceleration in the y prime direction. I'm taking that to be zero. And that, in fact, gives me that Fn minus mg cosine theta is equal to 0. So the normal force is, in fact, mg cosine theta. So there's part of my answer. Specifically, that's the normal force part for part A. Now, uh, notice the weight technically just pulls straight down, but I asked what force makes the box slide down the incline. Well, that's the mg sine theta. So that's the force that causes the mass to slide down. So I can say now that force to slide is W sub x, which is equal to mg sine theta. So that's part B. And if you watch season 1, episode 1, the pilot episode of Big Bang Theory, you'll learn that Leonard and Sheldon get asked to go pick up Penny's TV. Or actually, if you look at episode 2, they get asked to go get a Swedish entertainment center or something like that. Somebody's supposed to deliver it, and the delivery guy just leaves it down the bottom floor, and then they try to work out some way to bring the box upstairs. Well, they look at the stair and they estimate the stair is about 30 degrees, and then they said, okay, well, the box probably weighs 100 pounds, therefore, if we tilt the box on the incline, it'll reduce it by a factor of sine theta. So sine 30 is 1/2. They're literally using W equals mg sine theta. So that's kind of interesting and neat to know. Now, if we want the acceleration, all we've got to do is take the summation of the forces in the x prime direction is equal to mass times acceleration in the x prime direction. This time, that one's not necessarily 0. So what I have is that mg sine theta is equal to m times a, and therefore you can see the m's cancel out, and the answer is a is equal to g times the sine of theta, and that is the actual acceleration. This is actually what Galileo saw, and that's why he used inclined planes to study motion. Anybody have any questions on that? All right, I've got one major problem that I want to solve. There's actually another one. There's a fuzzy dice hanging from a rear view mirror that teaches us another technique. You can do a Google search for fuzzy dice on my YouTube channel, and you'll find me working that. Or you can just look at the example in the book. I don't think I'm going to have time to cover it, so I'm going to jump to the Atwood machine. Now, the Atwood machine is basically a pulley that's massless, and hanging from it is a mass. And I'm going to draw this with a big M to make it appear like it's the heavier of the two, like that. And then I'm going to take another rope. Oops. Why is this not doing it? Ugh. Okay. So over here is going to be a mass little m. And I'm just using that because it's obvious that when someone writes a big M, that they might assume that one's the bigger of the two masses, and then when they write a little m, they might assume that that's the smaller of the two. This pulley is massless, and the rope is massless too. Now, what that does is the pulley being massless means that the tension on the left-hand side and the tension on the right-hand side have to be equal. Because if the pulley actually had mass, if I pulled the big M down, I would be responsible for not only lifting the little m up on the other side, but for also rotating the massive pulley. Whereas if I just grab the rope on the left hand side and lift it up, I would only need to lift the mass M up. I don't have to also rotate the pulley. So you see that in that case, if the pulley had mass, the two sides would have different tensions. So by showing that it doesn't have mass, we then showed that it does not have two different tensions. Also, the tension would be different at different lengths of the rope. So, for instance, right here, the tension be very small because I only have to move this little piece of rope plus this M. Whereas if I was up here, I would have to move all of this rope and the mass M. So that's why we assume the pulley's massless. Now I'm going to draw my free body diagrams really quickly. And the way I've got this set up, it looks like the big M is going to be coming down. So I'm going to choose that as the positive X direction. So this is my coordinate system for big M. And this is in fact going to be my x-axis. And I'm going to treat downward as positive, which means that this force right here, W equals mg, which I'll call W1, that's the force pointing downward, and that's the positive one. Now, if you ask the box, it would say, yeah, I would fall at 9.8 if it wasn't for the stupid rope slowing me down. So, with that in mind, you think, oh, well, the tension in the rope, which I'm just going to call T, that's what's slowing me down. So now I can say that Newton's second law gives me mg minus T is equal to MA. Notice by treating one object at a time, there's no ambiguity as to what mass to put on the right side of Newton's second law. If you tried to treat this whole thing as one big object, it would be a little confusing, so I don't recommend you do that. Now I'm going to draw a free body diagram for the little m. Now, when I pull down on the right hand side, that causes m to go down, which is the direction I expect everything to go, but that causes little m to go up. So if I don't want to make an equation that relates the acceleration of little m to the acceleration of big M, then I need those two coordinate systems to agree. So what I'm going to do for the other mass is I'm going to assume that the x direction is upward. So in this case, I've got a mass little m, and in fact, the tension in the rope T is positive on this side, but the weight of the mass little m is W2 equals mg. That's the other force. So using Newton's second law, I now come up with T minus mg is equal to ma, and that's equation 2. So one of the reasons I'm showing you this Atwood machine is showing you how to break the problem up into two separate parts and make two separate free body diagrams. But another reason is to show you the techniques that we need in this physics class to actually solve a system of equations. We just saw 3 equations being solved when I did the train of boxes. Now I'm going to see 2 equations. Well, one of the ways that you learn for systems of equations, you might not remember it from pre-calculus, but it would be like you could take one equation and multiply it by a number, take the other equation, multiply it by a number, and then by doing so, you've now made the coefficients of one variable positive, 5t, and the other one's negative 5t. Then you could add them, and the positive 5t and the negative 5t cancels out, so you've gotten rid of the variable t. That's what we're going to do here. If I look at equation 1 and equation 2, if I were to just add them, the t's disappear. So that's what I'm going to do. Let's say add equation 1 to equation 2. So when I add the two left sides, that's going to give me mg minus t plus t minus little mg. That's adding the left-hand sides. So this minus t and this plus t are going to cancel out. Now, adding the right-hand side gives me ma plus ma. So I might as well factor out the common a. So I'm going to write this as m plus little m times a. Not only that, I'm going to go ahead and see that I have a common factor of g in what's left on the left-hand side. So now I'm going to say m minus m times g is equal to m plus m times a. Therefore, a must be equal to m minus m over m plus m times g, and that's the acceleration. Okay, notice how I wrote it as a dimensionless quantity multiplied by something that has the units that I want. Since g has the units of acceleration and I'm solving for acceleration, that was a really good choice here. That's a very common way to do it. Now I can plug, let's say this, plug a into, let's say, equation 2. And that'll allow me to solve for t. So equation 2 gives me t is equal to uh, m times g, or actually m times g plus a. So I can go ahead and plug in a there, and I'm going to get, notice the a is going to have a common factor of g, so I'm going to pull that out in front. But for g, I'm going to write m plus m over m plus m, because that's just 1 and I'm getting ready to factor out the g. Now, the a is m minus m over m plus m, and then it's times g. So now you see that I've basically factored out this g. Let me write above it in case anybody's confused what I'm doing. I'm basically saying this is m times 1 plus a over g times g. That's essentially what I did there. And notice this m plus m over m plus m, that is 1. So now I can combine like terms, and I'm going to get mg times m plus m plus m minus m over m plus m, like that. You can see that the m and the minus m cancel out. And in fact, what we're going to get is t is in fact equal to, let's write it this way, 2m over m plus m times big M G. So that's the tension in from the Atwood machine. Anybody have any questions on that? All right, we're done. Class, we have finished all of this. We're finished with chapter 4, in fact. I will probably still take questions. I mean, I'll definitely take questions again on Monday. But there's another example that y'all need to look at. That's the fuzzy dice hanging from a rear view mirror. That's another technique of solving systems of equations. In that case, you're going to divide one equation by the other. That's something you never learned in your math classes, so I wanted to make sure you cover that. But what I'd recommend you do is just do a Google search for fuzzy dice. Just do a search for fuzzy, F-U-Z-Z-Y, and you should pull up me solving one of those problems. But you guys are free to go. Make sure you chat me your first and last name if you haven't done so already. And I will see you all next time. Do not forget to take your your online test by Tuesday at 11:59 p.m. And don't forget to figure out how to get a proctor for next week because you'll have Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, and Monday. Those are the only days you can take your face-to-face test proctored. I will proctor it for you on Wednesday if you want, but you'd have to come to the Virginia Beach campus. And you could also come to any other TCC campus and they'll do it at their testing center for free. You just have to call them and find out what their times are. Every campus testing center offers one night a week that it's a night testing time. So you might just need to figure out what campus is free on your night and then do that one. But just keep that in mind. They all have a nighttime testing, and some of them even meet on Saturdays. So you could, in principle, have a test taken on Saturday. But you guys got to do that on your own. So let me know if you need any help, and you guys are free to go. Thanks for coming, everybody.
Does the test have a time limit, the face-to-face one?
Uh, it's a pretty large amount of time, like it's on the order of 75 minutes.
Okay.
But yeah, and that's the same thing with the online test. The online test, you have a little bit more time restriction because I really don't want you looking up more than one question when you're doing an online test. If you're looking up more than that, you're not really for it. Also, remember the online test, you get multiple attempts and only your highest score counts.
Okay. Thank you so much. Have a great night.
You're welcome. See you, Michelle. Anyone else? Aiden, do you have any questions? All right, looks like they might not be here anymore. So I'm going to say bye-bye.